Welcome back, guys. This is another AP Chemistry video, and today we are going to do an introduction to stoichiometry. So it's just going to be the basics. It's something you should be familiar with from your chemistry class a couple years ago. But just to review, let's start out and remind ourselves that stoichiometry is the study of quantities of materials consumed and produced in chemical reactions. All that means is if we're doing calculations with a chemical reaction, they're usually referred to as a stoichiometric calculation. We're looking at the products, we're looking at the reactants, and we generally need to do a few calculations in order to change our products into reactants or our reactants into products and see how much we should end up with. Just a brief reminder. Let's talk about Avogadro's number. We know that it's 6.022 times 10 to the 23rd units of whatever you have. It could be 1 mole of eggs, it could be 1 mole of marbles, but we typically use it in chemistry to refer to a certain amount of a particular element or compound. That way, it allows us to change extremely lightweight materials. If you have 1 mole of it, it's so much that it allows us to weigh it in grams. And so 1 mole of carbon, or 6.022 times 10 to the 23rd atoms of carbon, would weigh its average atomic mass of 12.01 grams. And that's true of any average atomic mass on the periodic table. If you have a mole of that element's atoms, you have its average atomic mass in weight. So let's go with our first problem here. It tells us, or wants us to know, what number of iron atoms are in 4.48 moles of a sample of iron. So let's go ahead here and select our pen. And if we do our calculation down here, let's start with what they give us, 4.48 moles of Fe. All right, and so we know that our units are going to have to cancel out. So if moles is on top, we want to put 1 mole down on the bottom. And then if we're trying to get to atoms, we don't need a molar mass, we don't need an atomic weight from the periodic table. All we need to know is how many atoms are in 1 mole. And like we said before, 1 mole of anything is 6.022 times 10 to the 23rd. Right? So we plug that into our calculators. We notice that our units here cancel out, and I should have written atoms here as well because that's our unit. That's what we're trying to get to. And so now if we plug that into our calculator, we end up with this number up top. So it's 2.70 times 10 to the 24th iron atoms. Now, let's go on to another example. Calculate the number of moles and the number of atoms in a 10-gram sample of aluminum. Okay, so this problem is a little bit different. Instead of starting with moles, we are starting with grams of aluminum. So this time, in order for us to cancel out grams, we're going to have to use its average atomic mass from the periodic table. So if we look up aluminum on the periodic table, you would find that its average atomic mass is 26.98 grams, and that's in 1 mole, right? You need to have 1 mole of aluminum to have this average atomic mass. So we put 1 mole on the top. Our grams are going to cancel out, and we're going to continue. Now, we could stop here, and we would get our number of moles. So if you want, at this point, you can plug this into your calculator. You would get an answer of, let's see, let's write it down here. It would be 0.371. So our answer would be 0.371 moles of aluminum at this point. So this does answer our first part of the question, calculate the number of moles, right? So here we go, this is our first answer. I'm going to continue the calculation, however, because we also need to get the number of atoms. And this will be just like what we did on the last slide. Now, moles has to cancel out because we need to get to atoms. So we're going to put 1 mole. And since we need to get to atoms, we must use Avogadro's number, 6.022 times 10 to the 23rd atoms. Put our equal sign here. And then we're going to plug this into our calculator again and get the final answer of 2.23 times 10 to the 23rd atoms of aluminum. And that should actually be a capital A. All right, and so there we go. We've solved this problem pretty quickly. We went from grams to moles, got an answer. We went from grams to moles to atoms and got our second answer over here. Now, if you want, I can provide you with this little helpful chart. You shouldn't need it because these are pretty straightforward calculations, but you always want to go from atoms to moles to grams. Or I guess this will be mass. Maybe you won't be going to grams, but you'll be going to some form of weight. And you might not always be using atoms. You might be using molecules sometimes. But anyways, you get the idea. You should always be going from here to here. Or if you're starting at grams, you want to go from grams to moles and moles to atoms. You cannot skip and go from atoms directly into grams, right? That is not allowed. You always have to make a pit stop here with moles, right? And sometimes you'll stop here and you'll be done with your calculations. It just depends on what your question is asking. So let's do one more example. This one's a bit more tricky because it's not actually asking us for atoms or moles or grams. So we're going to have to see what we can do here to manipulate what we know and try to arrive at the correct answer. All right, so it says isopentyl acetate, C7H14O2, is a chemical in bee stings. Calculate the number of carbon atoms injected when 1 times 10 to the negative 6 grams is released by a bee sting. So we can only start with the number that they're given us, which is 1 times 10 to the negative 6 grams, right? And if we're starting in grams, the only place that we can go to is moles. So we want to get to moles first, and we want to get to moles of isopentyl acetate. And I'm not going to write that out because I have limited room here, but you should always keep track of your units and write that out. But I'm going to leave it off for the sake of space here so we can finish the problem on this page. So on the bottom, well, we need grams to cancel out. And that means we need the molar mass of this guy up here. We need the molar mass. If you remember from Friday, that means we need to add up 7 carbons, 14 hydrogens, and 2 oxygens. And if you do that all together, you should come out with a molar mass of 130.18 grams of carbon. Okay. That's not carbon, I'm sorry. 130.18 grams per mole is the molar mass of isopentyl acetate. So now we can put our 130.18 down here in 1 mole. So we have grams that cancels out. We have 1 mole at the top, and we can move forward with our problem. Now we need to go from moles to molecules. We can't go to atoms of carbon yet because we first need to get the number of molecules of isopentyl acetate. So we're going to put our 1 mole on the bottom, and we should all know by now that 1 mole of anything is 6.022 times 10 to the 23rd, and in this case it's molecules. All right, and we continue on. Our moles cancels out. Now we're into molecules, which is normally where the problem ends. However, this problem wants us to know the number of carbon atoms, right? In each one of these molecules, we have 7 carbon atoms. So that means we need to add 1 more step onto this problem. And we need to put our molecules down on the bottom. So in every 1 molecule, for each molecule that we have 7 carbon atoms. All right, and now our molecules cancels out, and we are left with carbon atoms as our final step, which is where we want to be. So plug this into your calculator, and you should end up with a final answer of, where did I put it? 4 times 10 to the 16th. 4 times 10 to the 16th carbon atoms. All right, this is our final answer right here. Okay, if you guys have any questions about this, please make sure you let me know in class and we can go over it again, or maybe a different problem and see how we arrive at our answers. Okay, only 2 more slides. This one I'm just going to skip through really quickly. We went over it in class, but just in case you need a refresher or you've forgotten how to calculate your molar masses, I've included a slide here. You can pause it. You can take a look at these different molar mass calculations and see if you can understand how I arrived at these answers. If you can't figure it out, again, come in before school or after school and let me know and we can work on solving our molar mass problems. But we should already have this down. And the last slide here, just another concept check. This one should not involve any math. Yes, you could do this problem solving all of the different A, B, and C for the greatest number of atoms, but we don't need to do that. Instead, we can show you the answer first. Let's read the problem here. Which of the following 100-gram samples contains the greatest number of atoms? Right? If we had 100 grams of magnesium, 100 grams of zinc, and 100 grams of silver, which one of them is going to have the greatest number of atoms? Well, we don't need to do any math to figure this out. All we need to know is their atomic masses from the periodic table. Silver is the heaviest. Since silver is the heaviest, it requires the least number of atoms to reach 100 grams, so it's not going to be silver. Zinc and magnesium. Well, between these two, zinc is going to be heavier than magnesium. Since zinc is heavier, it takes less atoms again to get to 100 grams, so it's not going to be zinc, which leaves us with magnesium. That's the lightest element, and so it takes the most atoms to reach 100 grams. All right, hope you guys found this video helpful. If you have any questions, again, please ask me in class or stop by before or after school and we can discuss whatever questions you may have. Thanks again, guys, and see you next week.